Okay, we're going to take a look at question 6. The concentration of dilute hydrochloric acid can be found by titration using a standard solution of barium hydroxide. 6.1. Calculate the mass in grams of solid barium hydroxide, MR of 171.3, needed to prepare 250 centimeter cubed of zero point 0.1 mole per decimeter barium hydroxide solution. This is worth 1 mark, and they want the answer in grams. Let's go. First of all, the question has asked us to calculate, so we know we're doing some maths here. It's given us the MR, and it wants us to find the mass in grams. So what do we know about mass in grams? Well, for mass in grams, you need to do MR times moles. You should know this off by heart from GCSE. So mass over MR times moles. I use that little n, lowercase n for moles. The second bit of information, we've been given the volume and concentration of a barium hydroxide solution. So you should also know the magic triangle from GCSE, number of moles over concentration times volume. So now what we need to do is use the concentration and the volume to find the moles, and then put the moles over in the second triangle, times it by the MR, and we'll get the mass. So let's have a go at that now. So don't forget, when you get centimeter cubed, you need to divide by 1,000 to put into decimeter cubed. So we're going to do 250 divided by 1,000. We're going to multiply that by 0.1, and that's going to give us our number of moles, which is lowercase n. We're then going to multiply our number of moles by the MR, which is 171.3, and that's going to give us our mass in grams. So 0.025, which is our moles we found from volume times concentration. And we're going to multiply that by 171.3, which is the MR of barium hydroxide. And now we're going to get our final answer, which is in mass. And it works out like 4.285. Okay, 4.285 grams. And there we go. Now let's move on. So for 6.2, the mass of barium hydroxide from question 0.61, that's 4.285, is dissolved in a beaker containing 150 centimeter cubed of distilled water. Describe, notice the word describe is different than calculate. So this is a written answer, even though we might make the mistake and think we need to do a calculation here. That should trigger you into realizing it's a written answer. Describe how the solution is used to make 250 centimeter cubed of 0.1 mole per decimeter barium hydroxide solution. So they actually want a description, not a calculation, even though there's some numbers here. So what we want to do is say add the solution to a volumetric flask. Okay, volumetric flasks have a mark, so we want to make that up to the mark by adding distilled water. Include all your washings. So that means get some distilled water and rinse out the beaker or whatever you made the original solution in, and tip all of that in so you haven't left any of the 4.285 grams left behind in your apparatus. You want that all to enter the volumetric flask. And then you're going to put the stopper in and invert several times, which means turn it upside down. You don't have to use the word invert, but basically rotate, turn it around once the stopper's in, and that's going to evenly spread the mass. And there you go. You've now got a solution. Oh, let me just add that in. I forgot to add the washings in. And there we go. So let's move on to the next part of the question, which is going to be 6.3. 6.3. Before the first titration, the 25 centimeter cube pipette is rinsed with a small volume of 0.1 mole per decimeter barium hydroxide solution. State why it's a good practice to rinse the pipette in this way. So we're not talking about a dropping pipette, we're talking about the volumetric pipette, the one that measures exactly 25 centimeter cube that we use for transferring solutions. Now, if we're going to put in it the known concentration, we mustn't rinse it with water. If we wash this pipette with water, it's the known solution. We're going to dilute it. And this means it's no longer going to be a known solution. It's going to have a lower concentration than we thought. Also, there might be some water left over in it. So you should always wash it with some of the known solution. That way, you're not going to alter the concentration at all. So wash it with the known solution. You won't alter the concentration. It will get rid of any water or any impurities in the pipette without diluting the concentration of the known. Of course, when you're dealing with the unknown solution in a titration, you can rinse and should rinse with distilled water, as you won't affect the amount of moles in there. All right, let's move on to 6.4. Hydrochloric acid is added to the burette using a funnel. State why it's good practice to remove the funnel from the burette before the titration. So let's have a little look. Okay, if you leave the funnel in there, which has got hydrochloric acid in it, as you do your titration, some hydrochloric acid might drip from the funnel into your burette. This means you'll get an underestimation or undervaluation of your titra. So you might think you've added 25 centimeters, but actually you've added 26 centimeters, and 1 centimeter dripped in from the burette and made you think you'd, from the funnel, 1 centimeter dripped in here in pink and made you think you'd only added 25 instead of 26. So you'll get an undervaluation if you leave the funnel with some acid or alkali in dripping into your burette. So that's why we got to remove the funnel before we open the tap and start the titration. Now that'll get you 1 mark. So let's move on to 6.5. In a different experiment, 0.952 grams of solid barium hydroxide is used to make 250 centimeter cubed of standard barium hydroxide solution. I can't even speak. 20 centimeter cubed of this barium hydroxide solution reacts exactly with 24.50 centimeter cubed of hydrochloric acid. Calculate the concentration of the hydrochloric acid. So what we want to look at here, we've been given some volumes here, which I've labeled V. I might want to label this M for mass. I've been given another volume over here, 250 centimeters. What I'm starting to gather here is that I'm going to need those triangles again, that N over C times V, and I'm going to need M over MR times N as well. So I'm going to need my triangles. The question is, calculate the concentration of the hydrochloric acid. So we're probably going to need to know the ratio. Whenever you're going to use moles, you're likely, and there's a reaction going on, you're going to need to know the ratio between the reactants. So let's work out the ratio between the barium hydroxide and the hydrochloric acid in this reaction to start with. Also, check this out. They'll always do this in titrations. They take a large volume, like 250 centimeter cubed, and then we're going to titrate just a 25 centimeter sample. This means when I work out the moles of that barium hydroxide, it's 10 times smaller than it should be. So we're going to work out the moles in the 25 centimeter, and then we're going to need to times by 10 to work out the total moles in the 250. All right, let's look at this equation. Barium hydroxide plus hydrochloric acid goes to barium chloride and water. Basically, base and acid make salt and water. We can see it's a 2-to-1. So for every mole of barium hydroxide we've got 2 moles of hydrochloric acid. So which one of these can we work out first? So we can work out our moles of barium hydroxide, and we can do that by doing 0.952 grams and divide it by that MR they gave us in one of the earlier parts of this question, 171.3. And that gives us 5.56 times 10 to the minus 3 moles of barium hydroxide. Now that was in the 250 centimeters. What we have to remember actually is that we only used a tenth of this. Okay, so actually we need to divide that by 10 because it's going to be a smaller amount that we actually used. We took 1/10, 25 centimeters from the 250. Sometimes you've got to times it by 10. In this particular question, we have to divide by 10 because we're taking a tenth of those moles in the 0.952 grams. So we're going to divide by 10. Then that's our moles of barium hydroxide. And that gives us 5.56 times 10 to the minus 4 moles of barium hydroxide. Now we know that for every mole of barium hydroxide, I've got 2 of hydrochloric acid. So we want to multiply that by 2, okay? And that is going to give us 1.112 times 10 to the minus 3. And that's our moles of hydrochloric acid. Now what we want to do is do N over CV. So we're going to do moles of hydrochloric acid divided by the volume of hydrochloric acid. Now, the volume of hydrochloric acid was 24.50 centimeter cubed. Don't forget to divide by 1,000. You need to convert to decimeters. And that is going to give us our concentration of hydrochloric acid. By doing N over V, we get C, and it is 0.00453. What's that? 8. Well, we can just call it 0.045. And that gets us 3 marks. So let's move on. 6.6. The final part to the question.
You're still here? It's over.